And we will be back in English, and I will welcome our CTO and founder, Srini, who will talk about how to bring generative AI to the next level through vector search with graph and key value analysis. And they will be helped with Berat, who will come with him later, principal solution architect at Aerospike.
Thank you, Pierre. I think I need oh, here it is.
And I think you will have your presentation quickly. Yeah.
Oh, I got the wrong one.
No. So some logistics. Perfect.
Okay, we're just going to wait. So while we're waiting, let me give you some context about our my presentation today. So Subbu talked about some of the basics of our platform, and Maxime gave a great presentation on how Criteo has taken advantage of those fundamental properties, essentially of providing very high performance, but also at very high scale, because the limits keep increasing. We saw that theme over and over again. The idea, you saw it in the BSV talk, that the limits which we can actually, or we need to actually support, continue to kind of increase over and over again. Even though I didn't follow a lot of the discussions in the panel, but I did get, I know a little bit of French from my high school. But what I understood was there's a lot of different areas in which people are modernizing. It's not only about legacy systems. It's also that if you don't adopt these new technologies going forward, essentially one runs the risk of being left behind. And that's essentially what we have been focused on, taking the platform that we have, which works great for the NoSQL use cases, as I call it, typically key value and some level of document-oriented use, data modeling, which have been used heavily in the ad tech space and other areas that Subbu talked about in financial services, telcos, e-commerce, and so on. But what we are doing now is adding more data models on top of it, like graph and vector, which is what I'm going to talk about today. And the idea is to bring the basic goodness of the platform, the various TCO advantages, the high performance, and also add more query layer capabilities, which is what Subbu briefly alluded to that, because the data layer for key value and document dominates. Not much of queries happen at that level, but then because we use indexes and so on, but with graph and vector, there needs to be a really robust distributed query processing layer. And that's what we use, for example. We have developed for graph, and we've also developed an equivalent one for vector. We will talk about it. I guess I seem to be running out of things to talk about. Okay, we are here. Perfect. Okay, are we good? Okay, thank you. So in this, okay, let me go back. So my name is, Srini Srinivas. I'm CTO and founder of Aerospike. Brian Bulkowski and I founded the company. In the early days, both of us wrote all the code. So, but then I don't think I understand most of the code anymore. But more importantly, the basic principles of Aerospike we have carried forward and enhanced over the years. I'm going to talk in this particular presentation. We're going to talk a little bit technical. We're going to talk about what vectors mean, and then I'm going to explain a little bit at the high level what vectors are, and the HNSW algorithm and the implementation of it, and how we can make use of a multi-model database like Aerospike, with various with NoSQL vector and graph to basically combine and write applications. And then Berat will follow it up with a demo of ours, of a real application. So why are vectors important? Because they allow you to essentially search on any domain. So I'm going to take you through a very trivial example. What you have is a domain. It could be like, I'm going to show an example of trying to find a house based on your criteria among the existing available houses. But the whole idea is you take whatever domain you have, you run it through an embedding model, and eventually you come up with a bunch of vectors, which is nothing but numbers, okay? And that's essentially what it is. And these basically capture the semantic meaning of the source data. The embeddings do the job. They find out what data is close to other. One of these instances on the left is close to other instances. That's fundamentally what it's trying to do. It is a lossy algorithm. It's really important to understand that. Vectors by nature, they could take like trillions of objects on this side and reduce it to billions of vectors, so to speak. And then you're kind of compressed everything. And then you can do very efficient approximate nearest neighbor algorithms, searches, and so on. So that's kind of the idea here. So I'll kind of illustrate it quickly using an example. It's a very simple example. Let's say you're going to search for a house. You want about 2,500. I don't know. In Paris, that might be very expensive. But in California too, it's very expensive. But people do look for these 2,500 square foot of floor area, and on a land area which is 6,500 square foot of land, so to speak, of the lot size. And we think that the floor space is twice as important as compared to the land area. Okay, this is the basic idea of the embedding. Okay, we're going to create an embedding, and then you have a bunch of, we have 9 houses there with different land areas and floor areas, and then it kind of gets distributed in this space. Okay, that's fairly straightforward. Which one should I choose, right, for what I want? Now, what you have to do is you have to turn each of these housing data into a vector, so you can actually do a search. So you go through this, and the way you do that is you take, for example, for the land area, you take the largest amount of land, and then you divide everything by that. You get basically a number for the normalized land, which is less than 1. Right, and the 1.0 is the largest one. Similarly, you do it for the floor area based on the data items. Right, I'm showing a very trivial example, so it gives you an idea of what it is that is required, and then you weight it, because since we think that the floor area is worth twice as the land area, we divide the land area numbers by 2. So now you have a vector which represents these 9 items. Then what you do is you basically, and this. I'm not going to go into the thing. We use a cosine similarity. It's basically a function which you can apply to this. But fundamentally, what you do is you take what we have, which is 2,500 square foot of floor space on a 6,500 square foot of land, and then you compute, basically what it is that you're looking for, and then use cosine similarity to find the closest one. And we find that the one closest to it is house number 9. Okay, and this is essentially the kind of math. This is not exactly a vector thing. This is kind of what you do. Okay, in order to find it, you basically take everything and convert it into a number, and then you find various, and there are many more algorithms, different embeddings you can use. So what exactly is a vector database? It's going to manage these numbers. First of all, you need to be able to store vectors in your database. Okay, that's actually the easy part. So when you see a lot of these databases going like, we support vectors, they're saying I can store a vector. The hard point about the vector stuff is, how do you search for it, okay, efficiently? And it is easy to search in a, like the example I showed is trivial. You can just simply essentially run up, look at all the 9 items that I have, and then you can go take what you want, and then you just go compare it with every one of them, right? That's not going to work when you're like Criteo and you have like, a trillion objects and various things that you want to search on it, okay? You just have to do better algorithms, and I'll talk a little bit about that. Essentially, the key features that you need from a database is the ability to ingest a lot of data. You need to be able to generate the embeddings, right? When you're given a problem space, you'll get a billion items, rows. You need to generate these vectors first, build an index, and then you got to take a request, and you store these various items in your records, so to speak, and then you can then search for it to find the closest one. It's an approximate search, and I'll come back to it later. An approximate search may not give you enough of an answer. That's why we want to combine vector search with key value as well as graph in areas. I think Subbu kind of showed a little example, and I think Behrad will show a demo on that. And there are many applications you can basically use this for. So how does this really work, right? So this is going to be a little I guess, technical, but I'll try to make it as simple as possible, given it's late and I'm standing between you and drinks and food. So I have to kind of, but I'll also be there at the break, so you can ask me more questions. The example I used worked well because the cardinality was small. It's just nine items. That's kind of trivial, right? Essentially, we compute the cosine similarity against every vector. We sort the results. You can't do this when you have billions of trillions of vectors. The computational cost is extremely high, and you will have a lot, it'll take a really long time to finish it. And we have this concept, which has been developed in the industry in research called hierarchical navigable small worlds. This is used extensively to solve these problems. Now, in order to get there, I want to kind of take you through a concept called a skip list, just to give you an idea of how you do this. In this example, you have a list of numbers, and you want to find a particular number. Let's say 225 is the number. I want to find the closest value to 225 on this. You could, of course, do a binary search on it, but we're not going to do binary search because it doesn't work great when the data is changing all the time. So you create what is called skip lists. These are many lists that you create. The first one skips all the way to the end, in fact. The second one skips to the item 237. Since we are looking for 225 is what we're trying to find, you always start at the top left. There are many levels of lists. Okay, so you basically say, can I find an item which is essentially, you keep going to the right until the item you're finding is greater than the key you're looking for. That's all we're trying to do. So this one, I think you just come down. Okay, in this case, it's the end of the list. You come down. Now you're here. What do I do now? The item to the right is 237, right? And I don't know if this will work. This doesn't work. So 237 is this item. So you got to come down again. And now this item is 68. 68 is actually bigger, right? I'm sorry, it's smaller than the key 225. So you're going to have to move right. But then it will stop again at 237. So you can't go further. You got to go down. And then you come down here. You're going to skip one more, right? And then you stop because this again is 237. So far, so good? And that's it, basically. You come down here, and then you can go up to 221, and that'll be your answer. Okay? So you now have these various layers. It's a one-dimensional thing. HNSW is a multi-dimensional thing. You can actually have, and this is the basic idea. Now you have layers. Okay? And this is it is log n. It works better than binary search trees because you can insert and then you can create these skip lists, and so it's all I think that's kind of why it is. So skip lists are one-dimensional. Sorry. Oh, okay. So skip lists are one-dimensional, and HNSW extends this to n dimensions. Okay, that's kind of the key. The higher levels have fewer data points. Therefore, you can just find, what happened? Okay, it's back. So higher levels have fewer data points. And then you traverse by finding the closest thing at the higher level, going down, and then finding the one at the next level, and then going down until you find a neighborhood, and then you go search a lot more. And that's kind of basic idea of how you find things. And then you find it at the top level and dropping down. Okay, and I kind of showed it to you in the single dimension of the skip list. You're doing the same thing with layers and multiple dimensions. So one HNSW search can result in thousands of data point lookups of very large data sets. This is very important. This is where all of the platform work we talked about, which are in the key value space, can be adapted to large vector databases. Okay, that's why Aerospike becomes a good fit. Similar thing also applies for graph, but I'm not talking about graph today. I'm just going to talk about vectors because graph was last year's product. We are still going to enhance it with other things, and then we'll probably have in the future have that. So for the Aerospike implementation of the HNSW, what is very good about Aerospike is we have very fast key value retrieval. It scales to a lot of data sizes, right? Very, very high databases. It's got very low latency, which we saw in Maxime's presentation, why that low latency was actually a fundamental reason, the high performance, right? And he talked about like 99% under 5 millisecond response time and an average of less than a millisecond. All of that we can bring to the table And also we are able to store really lots of data very fast. We can ingest, and we will store the application data, which is basically a bunch of vectors. We'll also store the vector search index in our storage. Okay, we're adapting our key value onto it. And the important thing is we have now the data layer, which is what is used heavily in some of the applications we talked about in the NoSQL space. We have added a query layer. Now, the query layer itself is distributed with multiple nodes, which communicate with each other. And this is important because, first of all, it partitions the vector index, and it also caches vector search off storage, because you can't go to the storage all the time, because vector indexes essentially have to go through these various layers. And for the same search, you might have to request the same data multiple times. And that data might already be in some other node in this particular query layer, and you would have to go back and forth. And that's really important to understand. The distributed technologies that we use in the data layer have to be adapted to the query layer in a different way in order to make vector and also graph. The same thing also appears in graph. So, and the cache the cache hit ratio for queries is important. And all of this has to be self-healing, right? If a node goes down in the query layer, we already know that Aerospike supports the nodes going up and down on the data layer. We would have to do the same thing for the query layer. I think that's something we have the technology of inventing that. So there's also a challenge in terms of changing, right? One of the biggest things about Aerospike, which is really fundamentally a game changer, is that Aerospike is able to write or take writes from applications at very high write throughput, while still having the ability to read that latest data. In order to do that for vectors, it gets a little bit more challenging. Why is that? Because when you build an index which has all these multiple layers, you could basically serialize every addition to the index. That will make this thing correct. However, there'll be a bottleneck if you do it by serializing all the writes to the index. What is a better way to do it is to parallelize writes to these various index components. But you know that the same component could be cached in various of these query layers I talked about, right? Query nodes. So that will cause inconsistencies. You'll be able to change the index fast, but it won't be correct. The index might be corrupt. So what do, right? The first one is not scalable. Second one is not correct. It scales great, but it is not correct. So we kind of combine the two. What Aerospike does, this is basically a solution we've come up with for our vector. Application writes to each shard are broken into batches. Okay, and then we take the HNSW, the index, and we partition the index across these nodes. So each one has, this is much like if you're familiar with the Aerospike's partition management for the NoSQL space, there are partitions which are owned by certain nodes, and a replica lives somewhere else. Okay, and this is essentially a similar concept here on the query layer. And then what we do is we partition the HNSW index, and then when you get an input, you send it to the partition, which essentially has to take that update. This works great because then you can do that in parallel. But at the end, though, you have to merge these things together. You do have to serialize at some point. And then that serialization will be not as onerous as the one you will have to do up front. So you partition the HNSW index, change the individual copies, and then eventually put them together. So essentially, you have to kind of adapt some of the distributed database technology at the query layer. Okay, that's basically what we have done. So let me go to the last part of the third section before the demo. Why is the multi-model database important? Because it allows you to use the right model for the right use case in the same data platform, right? And that's really important because and this is how you would do it in vectors. So the Aerospike existing record, and the good thing, right? Graph slightly different, but with vectors it's very simple. You create a vector data type, just like we have sets. We have what do you call it? Various floating point numbers. Various types in the data. You can have a column which is basically a vector. And you could have many vectors, right? If you have a particular record, you can treat that in multiple embeddings. You can create different vectors for that record, and then you can and then create a different each of those embeddings, and then you will end up being able to do multiple searches on vectors. And then that's essentially what this will do. And this will actually all be stored in the storage layer, but the query layer will also cache the vector index, as we talked about already. Okay, that is the basic way in which we implement this in Aerospike. And then vectors and graph actually work well together. Essentially, what happens with vector is the semantic search. It's an approximate thing, right? So you find things which are close to each other. You don't necessarily do an exact search query. You will get like things in like blue shoes. You'll get a bunch of blue shoes, okay? And that we can map to. But then is it exactly the one that you want? And then if you actually have a graph, it stores the actual relationships. So vector basically creates these relationships using semantics on an entire space. Graph physically has those relationships stored, which means there needs to be, that's fairly easy traversal in graph. There is no traversal in vector. You just basically go find out what is next to each other, and then you'll get a bunch of nearby objects. And then you have to then potentially use graph or a key value query to find more of the data and resolve the actual answer. And exact match searches, of course, are available in graph, not so in vector. But so you put it together, right? So what you can do is you can put together key value. This is the kind of I'm giving you a preview of the kind of the demo. This is an e-commerce application. You could actually look at the catalog that you have and essentially find out items that you're interested in. And then you could basically find similar items, using various, you can use natural language search. You can basically show similar items based on the vector, embeddings that you've created and the index that you've created. And then you can use the traversal for once you find the similar items to find all the actual people, what other items have they bought if they bought this original item, which is similar, right? So now you have actually the ability to put all of this together in one application with data stored in a single platform. I think that's the thing. That is the takeaway in this, okay? So, and it will scale and so on. There are various kind of trade-offs in terms of single model versus multi-model databases. Typically, if the theory is that somehow the single model databases will be better because they are focused only on one model, okay? But that is not entirely true because every single model database will have to implement a data layer also. Now, if you are like Aerospike, and Aerospike has implemented such a highly performant data layer, it will be applicable to multiple models, and that's literally what we have found. We have done, not just us, but our customers have done performance analysis of our graph implementation with native graph databases, and we scale better, we have higher performance, and so on. Okay, and the same thing we hope to demonstrate on vector also. Okay, so that's fundamentally there are advantages of multi-model databases. So again, this is exactly, I'm going to go back to Maxime's point, which is like you have Aerospike, you're not compromising on performance, but you're still getting the functionality. Okay. Compared to other key value databases, we are attempting to basically replicate it, and we have, I think, already replicated it for graph, and the same thing is going to happen in vector. And those are the things I'd like you to kind of take away from this talk. And I think you've already seen this picture, Subbu showed this. Fundamentally, it is the same platform on which we have built all of these data models, and therefore, you should get the benefits of the platform. That is our basic intention and what we are working towards. Now, I'm going to hand it off to Behrad, who will show us the demo. Are there any questions for me before the demo? Or okay, there is one. You want to give it?
Thank you. So I'm Victor from Criteo. So I had a question on your solution. Is it possible to do filtering? Because usually we have a lot of partners, or maybe we would like only to get your example, you have houses. Maybe you want to find the one that fits, but that has a price which is below a constraint. Do you handle that in your model?
Can you hear me? Okay. Yes. That is the idea of filters. So what you do is you basically get all the houses nearby, and then you can do it one of two ways. You can first find all the houses using a secondary index query, which are less than the price, and then you can just go physically look at all the list and then compare the vectors, see which one is close. Or you can, if there are too many being returned that way, you go to the vector search, find the closest ones, and then you filter the price. So you have two choices. I mean, and this is something. This is the advantage of having all of them in the same database. So you can pick and choose based on the cardinality of the query, and so on and so forth.
I can also add something to this. We are also thinking about creating multiple indices based on what you want to do. So if you want the accuracy for just one single customer that you have, that you only look into their data, you can just use that specific index dedicated to that customer. So you can have either one single index that is shared between everybody, and then we are going to use a filter basically to use to fetch the part of the data that you are interested in. Or if you say that this customer's data never going to be mixed with someone else, you can only create index for this customer and index for another customer, and therefore your search is going to be specific to that customer. Just as I know the context with this question.
Okay, thank you. And I guess I get all my answers. Maybe if the filtering cost is 25%, does it mean that the query time will be time 4?
Please.
Will it take more time if the filtering constraint is high?
If the constraint is low, you mean? Because if you get too many results back, is that what you're saying?
No, I'm saying that we are doing a query, but we have so much constraints that maybe the index is going to take so much time to answer, and it's going to impact on the 99% tile latency, for instance.
Okay, hold on. So if you're going to do a vector search, then we're going to have to do the traversal, right? So there are two problems we have to solve. One is the latency of the query itself, which is what you're asking about. The second is the quality. So there is basically a kind of a, what do you call it, trade-off between if it's higher quality answer you need, it will take a longer time. But then you're going to have to decide how, what is the quality of the answer, the confidence, level, how good it is, and then how much latency. So you'll be able to trade off these things based on a specific query. And that's important. Okay, those are the kinds of things which are really important in vector search. It's quality and latency, right? They don't necessarily go together. But I think we can get, given the performance, and the other part is actually ingestion. So if the data is changing, you want to actually get the more accurate, like a new house showed up in the example, and that's actually supposed to be better fit. What you don't want is the next query you run better take that house into account also, right? Otherwise, you'll be always behind, which is not a great thing to be. So there's the ingestion piece, there's the quality of the query, the results, and then there is also the time it takes. So you're going to have to figure out how to trade that off. But we hope to be able to provide you a single system where you can get potentially the ability to do all of those. Okay, any other questions, or we go to the demo? Okay.
Okay, thank you very much. I'm trying to be very quick so we can get to the drinks and food as soon as possible. So we have two demos here. First one is a RAG pipeline. So basically what we did, we used the data that we have in our blog and in our documentation as the input to the model. So we took the documentation, we chunked the data that we have, then we pass it to an embedding model, and then the result of the embedding model is a bunch of vectors. We put these vectors in Aerospike vector database, and then we create an application using different technologies and an LLM to basically search the database, search the vector database to answer questions that are, well, can be a little bit elaborate, and it can explain the result. It's not like a Google search, it's more like a OpenAI ChatGPT search. So let me quickly show you that. So for example, I can ask, is caching a good idea? And this is the result. So as you can see, it took it around 10 milliseconds to search for this result. This first article, I wrote that. That's why I'm asking this. So yeah. So, but as you can see, it's going through the first 3 articles that are about caching in Aerospike, and it's fetching informations. And you can make it more specific. You can ask different questions to get other parts of the information from the model, which is very interesting. It's relatively simple to make something like this. You can very easily just give your data to a model and store the resulting vectors in Aerospike and do this. So that was the first demo. The second one is a retail demo. We used a bunch of products. It's basically fashion items, and we inserted this data into Aerospike database, and we also used another embedding model to create vectors and put them again in the same record. So the record contains the information about the product, and also it contains the vector as well. We also have this information in our graph as well, and we created a holistic application using Aerospike database, Aerospike platform, which is which demonstrate the multi-model capabilities of Aerospike. So for this one, so the website looks like this. We have a bunch of fashion items. You know, there are different things, but let's say I want to search something that is not necessarily specific to the items that I have in the database. So let's say I search for blue suede shoes because I'm a big fan of Elvis Presley. So as you can see, the model is able to fetch shoes that are similar to the thing that I described I'm interested in. So this search is the result, is a vector search result, but the items that you can see are basically the rest of the record that is connected to the vector that is found. If I double click on any of these shoes, let's go to this one, you can see the rest of the information related to the blue suede shoes that are found. Also, here you can see some similar items. The similar items are fetched based on the picture that is available in the item that I'm looking at, and also the description of the item. So as you can see, some of these items that are here were not necessarily in the first search that I did, but these are very similar to the one that I'm picking up. So this is a result of the vector search. But also, we have another section here, which is also bound. So these items are usually bought together. This is coming from our graph database. So it says that, okay, this item was bought by these people, and these people also bought these items. So you're able to fetch all of the data, again, from the same platform. You don't need to distribute the data across different places. Another thing that is interesting here is that we have a breadcrumb at the top of the page that says that this item is a footwear, is a shoe, it's casual, and it's a Timberland shoes. So we also have secondary indices in the base, in the core database. Another thing that you can do is that you can click on this using the secondary index. It's able to fetch all of the items that have that tag. So now you can use a secondary index item as well. So I just want to show something else, which is quite interesting. So this website doesn't sell any coffee, right? But if I search for coffee, this is going to be the result. As you can see, none of the items are coffee. But look at this. This is an earring that looks like a coffee bean. Right? And this is the basically power of vector search. You can find something that is not necessarily similar to what you wanted, but has some characteristics that are similar. And as you can see, now that I'm searching for this, although I search for coffee, the items that are showing up here are earrings that have some similarities, some other similarities to the earrings that I got as the result of my search for coffee. So that's it. Thank you very much.